failure mode of tension member. Before learning about how to calculate the strength of a tension member, we need to know the failure of a tension member. Only if we know the failure pattern, we can able to identify the strength so that failure won't happen in a tension member. As per IS 800 2007, failure may happen either by yielding of a cross section or rupture at a critical section or block shear failure. These are the three predominant mode of failure in a tension member. If you look at the table 1 which is given in IS 800 2007, E 250, Fe 410, WABC are the mild steel which we use often in the steel structure, whose yield stress is almost 250 if the thickness is less than 20, and 240 if the thickness of member is 20 to 40 mm, and 230 if the thickness of member is more than 40 mm, and whose ultimate tensile stress is 410 Newton upon mm square. And if you look at the elongation, the percentage of elongation is 23. If you apply the load in a particular member, and if look at this member, if the elongation in this member alone increases to 23%, then what happens to the structure? Is this structure looks similar structure as it is designed or as it is constructed? No, it won't. So if this member expands 23%, what happens to this member? What happens to this member? And also this member? What happens to the joint? So it will pull all the member, and all the member is under stress only because of the percentage of elongation which happens in this member. It won't deserve the purpose for which it has been designed. Now in this picture we have a rod whose length is L0 and it is subjected to a tensile force. And in that experiment we have simultaneously drawn the stress strain curve, and here are the different pictures of this same rod at a different stage. So when it reaches the yield strength, the length of rod has increased. So some percentage of elongation has happened even at this stage, where it reaches the yield strength. And if you keep on applying the load, then it reaches its ultimate tensile stress, where now your cross section starts to decrease, and the necking formation happens in this zone. Then finally the rod will fail at a cross section where it is weak. So this is the yielding failure. At the yielding strength itself, the percentage of elongation is approximately 10 to 15%. So that is why we consider yield strength itself is the governing strength of a tension member. So if it crosses yield strength, then at that stage the percentage of elongation might be 10 to 15. So that itself is considered as the failure. That is why, even though it is a limit state method of design, here we use yield strength as the design strength of the tension member. And in that sense, we consider yielding is also a failure of a tension member. And second, rupture at a critical section. I have a few pictures that we did in our lab to check the strength of the connection and the tension member, and the plan of the connection is here and the cross section. So this is a lab joint. One plate is at the bottom, the other plate is at the top. The joint is connected using a bolt. And this is the failure pattern. We have applied a tensile force on this plate, and we have examined the failure pattern of the tension member. In the end, it has failed by the rupture. So wherever we reduce the cross section, because it has to be connected. So if you are using a bolt or a rivet, so there is no other go. You need to make a hole in the tension member, then you have to connect it. And if you look closely, this cross section looks like this. Okay, here is a hole, and we have made to insert a bolt or a rivet. So this is the effective area which resists the applied tensile force. So there is a reduction in the area wherever we have a hole. So that is the critical section for a rupture. And if you look at this picture, we have a chain pattern and a zigzag pattern of the bolt arrangement. And in chain pattern, we arrange whatever the number of bolt required in a single chain. Like we have a number of chains, but all the bolts are arranged in a row wise. But if you look at the zigzag pattern, the bolts are arranged in a zigzag pattern, okay? So that means one bolt is here, the other bolt is here, again one, the other bolt is here. It has been arranged like this. If you look at the rows, so one bolt is here and the other bolt is there. Okay. So that is the zigzag pattern. So there is an advantage of arranging a bolt in a zigzag pattern. Okay. Third is the block shear failure. And it is the connection where the block shear failure has happened. If you look at this connection, we have 8 number of bolts to connect the tension member with the gusset plate. The periphery of the connection has sheared off from the gusset plate. That is the block shear failure. In block shear failure, there are so many pattern of failure. So one can happen like this. So the periphery of the entire connection can shear off, and it can even happen like this. So where this member has sheared off, and it can even happen like this. All these are block shear failure. And if you look closely, here is the direction of the load, and whatever the member on this side and this side, it is subjected to, that cross section is subjected to shear force due to this applied load. So this cross section has sheared off from this member. And if you look at this cross section, it is completely subjected to a tensile force. So this cross section is subjected to tensile failure, and this cross section is subjected to shear failure. In a block shear failure, both has happened. Both shear and tension has happened. And see, I have a few YouTube videos that explains the animation of this failure pattern.